We continue on the material balance for the reactive system. For this case, we will consider the purging system. The purging system is used to prevent the steady-state accumulation due to the recycled steam, and there is inert or insoluble substance in the feed. For example, like this, for this case, we have the freeze. We have some fresh feed. That is include oxygen and inert also. And then you have some recycle. With recycle, you split the gas, right? As oxygen, nitrogen, and also something. We would put some substance to prevent the steady-state accumulation or some from the product stream. That's right. We separate into input system and recycle system. For this case, this for example, right? This is the motive we use to prevent the steady-state accumulation and to recycle steam and also the inert in the feed. We have to split inert to the feed, and also we would like to split it out of the product also. For that case, we use like this. It's also the example. Okay, for this case, we consider the recycle and purge system in the synthesis of methanol. The methanol can be produced by the reaction of carbon dioxide and hydrogen. To produce methanol in water. The first feed to the process contain hydrogen, contain carbon dioxide, and contain 0.4 mole percent inert. The reactor effluent pass to a condenser that remove essentially all of the methanol and water form, and none of the reactant or inert. That's right. Okay, the latter substance like the non-reactant, the reactant and inert. That's right. We recycle to reactor, and also to avoid the build-up of the inert in the system. The per system is withdrawn from the recycle. Okay, you can draw this is the recycle. We have the feed mixed with the recycle, and we have a reactor and product out of reactor, and also we send the product to the condenser. Of the condenser, we have two streams. The product is methanol and water, and the product is separated in recycle and purge, something like this. Okay. The feed to reactor, the feed to reactor is not the fresh feed. The fresh feed is feed to the process. The feed to reactor in this is the feed to reactor. It is the fresh feed to the process. The feed to the reactor contains 28 mole percent CO2, 70 mole percent, 28 mole percent CO2, 70 mole percent hydrogen, and 2 mole inert. It feed to the reactor. And the conversion or single part conversion of hydrogen is 60%. This means the conversion of hydrogen is feed into the reactor and output of the reactor. And then the question is calculate the molar flow rate and molar composition of the fresh feed. Total feed to reactor, the recycle steam, and the per system of methanol production rate. So this for the production is 155 kilomole of methanol per hour. Okay. The first step, we have to make the basis. For this case, you can base it based on production rate. You can do for this, but for the simple or the easy to calculate, for this case, you base it based on the known composition of the feed. But for this case, we base on the feed to reactor. You know the feed to reactor, the composition, and then you can assume the feed to reactor is 100 mole. And then after you solve for unknown, you can convert from based on 100 mole of fresh feed and to the based on production rate of methanol. Okay, we talk to you later. Okay, from the problem statement, you know the fresh feed to reactor composition. 28 mole percent CO2, 20 mole percent hydrogen, and 2 mole inert. That is feed to reactor. And also you know the composition only 0.4 mole inert in the fresh feed. The fresh feed we consider of carbon dioxide, hydrogen, and inert. But for this case, you know only the fraction of inert is 0.4% or equal to 0.004 mole inert per mole total. And also for the fresh feed, we denote NO is the mole to the process, and XOC is the mole fraction of CO. That's right. And mole fraction of hydrogen is equal to 1 minus mole fraction of CO minus mole fraction of inert, which equal to 0.996 minus mole fraction of CO. And okay, the feed two reactor, you know the composition and basics 100 mole. The output of reactor that include CO, include hydrogen, include inert. That's right. Inert feed two reactor equal to output because in there's no reaction. The input is 0.02 mole inert per mole. That equal to 0.02 multiplied by 100, you get 2 mole inert. And entry as mole methanol. N4 is mole water. That's right. Okay. From the reaction, it includes CO2, hydrogen, methanol, and water. And then send this product to the condenser. That's right. The condenser we have two steam. The first steam is methanol and water separated in the bottom. That's right. And another product is includes carbon dioxide, hydrogen, and inert. So we denote as N5 for total mole of this steam. And X5C is mole fraction of CO2 and X5S is mole fraction of hydrogen. And mole fraction of inert equal to 1 minus mole fraction of CO2 mole fraction of hydrogen. And the product stream we denote as N3 for methanol, N4 for hydrogen for water. That's right. And also this stream is separate into. That's right. The first stream is recycle. The second stream is purge. We denote the total mole is NP for purge, NR for recycle. That's right. NP and NR is the same composition. That's right. This stream is the same composition but different in amount. Like this. Okay. X5C equal to X5C from the purging and recycle is the same. It's the same is out of the cell condenser. X5S of hydrogen is the same. And inert is the same. But this is the same composition. This stream is the same composition but different in amount, like this. Okay. And okay, you draw the flow chart complete already. And then you have to make like the degree of freedom. The first step we will consider like the overall process. This is the overall process. Okay. For the overall process, you have how many unknown? N0, 2 XOC, 3 N3, 4 N4, 5 NP, 6 X5C, 7 X5. We have 7 unknown. That's right. We have 7 unknown. And we have 1 reaction. If you balance based on species, you have 5 independent balance species. And 1 inert. That's right. 1, 2, 3, 4, 5, 6. You get 3 degrees of freedom. For this case, you cannot solve for all of the unknown by overall system. Okay. The next step, you will consider the mixing point. For the mixing point, we have NO, N0, OC, NR, 5C, yes. 1, 2, 3, 4, 5. 5 unknown. That's right. We have 5 unknown. And 3 independent balance equation, carbon dioxide, hydrogen inert. Carbon dioxide, hydrogen inert. That's right. And the degree of freedom is 2. You cannot solve for this. And then you consider reactor. Reactor, you consider N1, N2, N3, N4, 4 unknown. And you can solve for 4 independent balance equation. That's right. Independent balance equation and 1 reaction, 4 unknown plus 1 reaction. Method 4 independent balance equation, CO2, hydrogen, methanol. That's right. And 1 single part conversion. You know the conversion. You have 0 degree of freedom. For this case, you can solve for that in 1, 2, and 4. Okay. This is the first step. You have to run on reactor. Okay. And then you consider condenser. Okay, for condenser, right? This condenser. You know N1, N2, N3, N4 already. That's right. N3 and 4 is known. That's right. because you based on reactor, you know N1, N2, N3, N4, and also N3, N4 is the same. This three be the same with the output. And you have remain N5, X5C, X3H. You have three unknown. For this case, you have three unknown and three balance equation: carbon dioxide, hydrogen, and inert. You have zero degree of freedom. Zero degree of freedom. You cannot solve for balance on methanol or water because this is not independent. Because the same amount is not independent equation. If you run on methanol or on water, you cannot do that because in this output equal to this output. This equation is not independent. Okay, you have only independent of carbon dioxide, hydrogen, and inert for this case. Okay, you get the second step. You solve for condenser. You solve for condenser, and then you consider the first recycle split in point. This point. Okay, for this point, your unknown is NP1, NR2, X5C, X5, S1, 2, 3, 4. 4 unknown. We have only 4 unknown. Okay, you know X5C, X5S already. Okay, sorry. You know 2 unknown, NR and NP, but we have only one independent equation. Why we have only one? Because you cannot solve for CO2, H2, and I because these three seem have the same composition. We have three balance equation, but this three balance equation is not independent. It's only one independent equation. For this case, is two unknown NR, NP. That's right. But only one independent balance equation is 1 degree of freedom. You can solve for that. And the next, you consider the recycle phase fit again. That's right. The recycle phase fit again. Okay, we count the unknown. That's right. NR1, N02, XOC3. We have three unknown. That's right. Three unknown and three independent balance equation. You can solve for that. Step 3. That's right. Step 3. Okay. And then you can balance per recycle split again. Step 4. This step 4. Because you know NR from step 3, and then you can solve for per recycle step, you can solve for NP. Yes, because you can solve for that. Okay. In conclusion, that's right. You not necessary to balance overall, that's right, because overall you cannot necessarily. The first step you balance on reactor. The second step you balance on condenser. That's right. And the third step you run on recycle phase fit mixing, and the last step you run on recycle splitting, and then you can know all of unknown for this step. That's right, for this step. Okay. For reactor analysis, that's right. For reactor analysis, we have one information with 60% single pass conversion of hydrogen. What does it mean? 60% of hydrogen convert and 40% of hydrogen unconvert. That you can calculate hydrogen output of the reactor. The hydrogen output is N2. That's right. N2 is hydrogen output. Feed hydrogen is 0.7 multiplied by 100 is 70 mole hydrogen. Okay. Okay. The unconvert hydrogen is 40% is equal to 0.4 multiplied by feed hydrogen. You get output hydrogen is N2. 28 mole hydrogen. This is based on single part conversion. And then you balance or so you balance on reactor analysis. The first step you balance on hydrogen balance. For the hydrogen balance, hydrogen is reactant. Okay. Input hydrogen, there is no input hydrogen. Output, input hydrogen, we have something like this. The general balance equation in minus out, that's right. Plus generation minus consumption equal to accumulation. For this set, there is no accumulation because it's steady state. For hydrogen is reactant, there is no generation. Okay, we get consumption. That's right. Consumption equal to input minus output, or output equal to input minus consumption. That's right. Output equal to input minus consumption. Okay, for hydrogen, that's right. For this case, we know like the hydrogen input, we know the hydrogen output. That's right. And you can solve for hydrogen consumption. Consumption hydrogen equal to input minus output. Input is 70. That's right. Output is 28. You get 42 mole hydrogen consumed. And then you balance on carbon dioxide is the same. Carbon dioxide is reactant. Output equal to input minus consumption. Carbon dioxide output is N1. That's right. N1. Okay. N1 equal to input carbon dioxide. Right, input equal to 0.28 multiplied by 100. You get 28. 28 carbon dioxide output minus consumption. From the consumption, you can compare to the limiting reactant is hydrogen. You know from the reaction is 3 mole hydrogen. That's right. 3 mole hydrogen consumed equal to 1 mole methanol. We consider like carbon dioxide. Okay, 3 mole hydrogen consumed equal to 1 mole CO2 consumed. That's right. 3 mole hydrogen, 1 mole CO2 consumed. But you know the hydrogen consumed is 32 mole. That's right. Mole hydrogen consumed cancel. Mole hydrogen consumed cancel is the mole of CO2 consumed. The same unit. And then you can solve for N1. 14 mole CO2. The next step you balance on methanol balance. The methanol is the product. That's right, is the product. There is no methanol input, no consumption, no generation. That means output equal to generation. For methanol, output equal to generation. The methanol output is N3. That's right, methanol output is N3. N3 equal to generation. You consider from the reaction, you know, like 3 mole hydrogen consumed equal to 1 mole methanol generated. But you know the feed of hydrogen is 42 mole hydrogen consumed. That's only the mole hydrogen consumed. You know, like the mole hydrogen consumed cancel. Cancel, you get mole of methanol generated. You get 14 mole of methanol. That's right. Okay. The next you balance on water. Water is also product. That's right. There is no water in the feed. There is no accumulation and there is no consumption, or that you get output equal to generation for water. The output water denoted as N4 equal to generation. From the reaction, you know, like 1 mole or 3 mole hydrogen consumed equal to 1 mole water generated. But you know the hydrogen consumed is 42 mole hydrogen consumed. That's why hydrogen consumed. That's how you get mole of water. You get 14 mole of water. So that's right. And then from the balance on reactor, right, you know N2, you know N1, N3, N4. 1, 2, 3, 4. And then you solve about the condenser. Condenser and IC. If you balance on total mole balance, input equal to output. That's right, for the total mole balance. There is no generation, no consumption for the total mole, and no accumulation for this case. And total mole balance is also the same by atomic balance. That's right, input equal to output. Okay. Total mole balance allow condenser, this condenser. Total mole input equal 1 N1 plus N2. That's right, plus N3 plus N4 plus 2. Yes. N1 plus N2 plus N3 plus N4 plus 2 equal to N3 plus N4 plus N5. That's right, plus N5. 1, 2, 3, 4, you know already. 3, 4, you can solve for N5. That's right. You can solve for N5. And then you balance on carbon dioxide balance. Carbon dioxide balance, you consider carbon dioxide. Carbon dioxide, we have two components, carbon dioxide N1, that's right, and carbon dioxide in stream N5, that's right. Carbon dioxide is X phi C multiplied N5 equal to N1. N1 equal to N5 X phi C. You know N1. You know N5 you solve for X phi C. That's right. And then you balance on hydrogen. Hydrogen balance around condenser. There is no reaction, that's right, in condenser. There is no reaction. Input equal to output and no generation, no consumption, no accumulation. Okay. Sorry. Hydrogen balance. The hydrogen input is N2. Output is X phi S multiplied by N phi. That's right. There is no hydrogen here. Okay. N2 equal to N phi X phi. N2 you know, N phi you know. You can solve for X phi S. And then you know X phi S, you know X phi C. You can solve for Xi. Xi equal to 1 minus X phi C. X phi S. You know, you solve for Xi. That's right. Okay, you need to know X phi C, X phi S, N phi. And then you solve for first feed recycle mixing point. Total mole balance of first feed. Yes. It's N0 plus Nr equal to 100. That's right. N0 plus Nr equal to 100. But this, you don't know N0, you know Nr. Okay, this is for the first equation. And then you balance on inert. That's right. Also input equal to output. This point is no reaction. That's right. No generation, no consumption, no accumulation. You get input equal to output. We have two terms, input of inert. Inert input based on feed. Feed is 0.004 multiplied by N0 plus 1 minus X phi C minus X phi S multiplied by Nr equal to 0.2 multiplied by 100. This is for inert balance. That's right, for inert balance. That's right, for inert balance. But this, you know, X phi C, X phi S already. That's right, you know X phi C, X phi S already. You substitute that. You can solve for N R and NO based on these two reactions. That's right. Okay. We have N0, Nr, N0, Nr. You solve in equation 1 and equation 2 simultaneously, you get N0 and Nr. That's right. And then you make the CO2 balance. CO2 balance input equal to output because there is no reaction around the mixing point. CO2 input is XOC multiplied N0 plus X phi C multiplied N equal to 0.28 multiplied by 100. That's right. You know X0 from this, you know Nr from this, you know X phi C. You solve for XOC. That's right. If you know XOC, you can solve for XOS. That's right. Because you know XOC, you know XOI already, you can solve for XOS. That's right. And then you balance around the recycle and positive around this. Okay. Total balance input equal to output, N5 equal to Nr plus Np. You know N5, you know Nr. You can solve for Np. That's right. For this, you solve for unknown already. But please note that this equation N1, N2, N3, N5, N6, Nr, Np is based on 100 feet of feed to reactor. And then you have to scale to the production rate of methanol. Because this process we will calculate based on production rate of 155 kilomole methanol per hour. Okay, for this case, you can multiply its total and component molar flow rate by the factor, right? From the balance, you know, like 14 mole methanol produced, and then you divided this to the 150 kilomole methanol per hour divided by N3, something like this, N4. You get this, the fraction from the real system is 150. For our system, from the calculation based on 100 mole feed to reactor is 40. You get the factor is 11.1. That's 11.1. You use this factor to multiply all terms. Multiply N1, multiply N2, multiply fraction, multiply conversion. And then you get the new value. This is based on 100 mole feed to the reactor. This is based on the production rate of methanol. Methanol. You multiply this by 11.1. That's right. You multiply this by 11.1. And then also the fraction is the same. The fraction is the same. You only calculate in the amount. That's right. This is a feed to reactor. The total is 100 mole. Based on 155 kilomole per hour of the methanol, you get this. You multiply this by 11.1. Multiply 11.1. 11.1. You multiply this by 11.1. That's right. You get the amount based on the production rate already. This is the scale up and scale down. It's easy to do that. Because if you balance based on 155 mole methanol per hour, it's difficult to balance that. But if you balance based on assume 100 mole of feed to reactor, it's easy to calculate. That's right. Please note that because all of this is based on mole percent, the fraction is the same. That's right. The fraction is the same. You not necessarily to multiply the fraction by 11.1%, something like you only modify to the total amount of each stream. For this, you can calculate. Right. I talked to you about the material balance on the chemical reaction process. And we balance on the single unit, multiple unit for recycle and burn. It's finished. But the next lecture, I will talk about the special case in the combustion reaction. That's like the combustion reaction. There are a lot of applications for this. I will talk to you for the next week. For this week, I will stop now for the lecture. Okay, thanks.